space is silent, vast, and far darker than it appears. Beyond the familiar stars lie cosmic voids, invisible matter. Wandering planets, violent stellar remnants, and regions where the laws of physics reach their limits. In this documentary, 10 terrifying discoveries reveal the hidden forces shaping the universe. Before the journey begins, take a moment to like this video, subscribe to the channel, and turn on notifications for more calm and immersive explorations of space. Now the descent into the darkest secrets of the cosmos begins. At the widest scale available to observation, the universe appears as an immense sphere of visible history. Earth rests near the center of this view only because every observer occupies the center of a personal horizon. Light arrives from all directions, carrying records of places that exist at different distances and therefore at different moments in the past. Nearby galaxies appear as they were millions of years ago. More distant galaxies appear as they were billions of years ago. The farther the light travels, the earlier the scene becomes, until observation approaches a time when the young universe is still hot, dense, and nearly uniform. This visible sphere is called the observable universe. It is not the whole universe. It is the region from which light or other signals have had enough time to reach Earth since cosmic expansion begins. Its size is larger than a simple multiplication of the age of the universe by the speed of light, because space itself expands while the light is traveling. The most distant matter now associated with the oldest visible signals lies tens of billions of light-years away in present-day distance, even though the light has traveled for less than 14 billion years. The geometry is difficult to picture, but the basic meaning remains quiet and clear. Observation is limited by time distance and the changing scale of space. At the edge of ordinary sight, galaxies become faint, small, and deeply red. Their light is stretched as the universe expands, moving from visible wavelengths into infrared and radio wavelengths. Telescopes collect these weakened signals with large mirrors, cold detectors, and long exposures. Each image gathers only a narrow portion of a much greater sky. Even the deepest surveys record scattered islands of light separated by darkness. The darkness does not always mean emptiness. It often means that matter is too faint, too distant, too cool, or too weakly connected to ordinary light for present instruments to detect. The oldest electromagnetic light visible across the sky is the cosmic microwave background. It forms a dim glow left from an early stage when the universe becomes transparent. Before that time, free electrons scatter light, repeatedly preventing it from moving far in a straight line. As the expanding universe cools, electrons join atomic nuclei, and light begins to travel more freely. That ancient radiation now arrives from every direction after being stretched into microwave wavelengths. It does not reveal a solid outer surface. It reveals a distant layer in time surrounding observation, because every line of sight reaches back toward the same early era. Small variations in this background glow show that the early universe is not perfectly smooth. Slight differences in density later influence the growth of large structures, yet the background itself remains remarkably even with a temperature only a few degrees above absolute zero. It is one of the strongest pieces of evidence that the visible universe develops from a much hotter and denser state. Its faint pattern becomes a kind of oldest accessible photograph, although it records conditions rather than familiar objects. Beyond that visible layer, the universe does not necessarily end. The radiation simply cannot provide a direct image of earlier times because matter remains opaque to light. Other messengers such as neutrinos or gravitational waves may in principle carry information from earlier conditions, but current measurements do not yet produce a complete picture of those remote stages. Scientific models describe them with increasing uncertainty as they approach the earliest fractions of cosmic history. The absence of direct light creates a natural boundary in knowledge, not proof of a physical wall. The observable region may be only a small part of a much larger cosmos. Measurements show that space is very close to geometrically flat on large scales. A flat or nearly flat universe can extend far beyond the region that is visible, possibly without any known edge. Current observations cannot determine its full size. They also cannot confirm whether the total universe is finite or infinite. Both possibilities remain compatible with some models, although each demands a different global geometry or topology. The question is not settled by darkness alone. This uncertainty produces one of the quietest and most profound limits in astronomy. Telescopes can look farther by collecting weaker light, but they cannot recover signals that have never had time to arrive. Better instruments reveal earlier galaxies and finer details in ancient radiation, yet the visible domain remains bounded by cosmic history. Knowledge grows within that domain while the larger setting may remain hidden. The darkness outside the observable universe is not an empty black region located beyond a distant shell. It is better understood as absence of causal contact. There may be galaxies, clouds, stars, and forms of matter beyond the visible range, but no information from them reaches present instruments. Their existence is inferred only through models that assume the large-scale universe continues beyond the horizon in ways consistent with the portion already measured. This assumption is reasonable, but it is still an inference. Within the visible sphere, every direction opens into the past. There is no single outer wall, no central platform, and no privileged line of sight. The farthest observable regions surround every observer in the same general way. A galaxy located billions of light-years away would possess its own observable sphere, overlapping partly with Earth's and extending into regions that Earth cannot see. The universe therefore contains many possible horizons, each centered on the place from which observation occurs. At this outermost scale, the darkest secret is not a hidden object, but a permanent limit, Most of reality may lie beyond direct view, separated not by distance alone, but by the finite age of the cosmos and the behavior of expanding space. Astronomy can measure the accessible light with increasing precision, reconstruct ancient conditions, and test how well physical laws describe them. Still, the visible universe remains a bounded archive inside an unknown hole. Its faintest edge is not the end of space. It is the end of the information that has arrived. Beyond the visible reach of the present sky, the idea of a cosmic horizon defines a limit created by time and expansion rather than by matter. It does not resemble a wall, a surface, or a distant border standing in space. It is the greatest distance from which information can arrive under the conditions of the expanding universe. Every signal moves through space at a finite speed, and the universe has a finite age. These two facts create a boundary around every observer, even when space itself may continue far beyond it. The horizon changes with cosmic history. In the early universe, light has traveled for only a short time, so each region can receive signals from only nearby places. As time passes, light crosses greater distances and more of the surrounding cosmos becomes connected. Yet expansion complicates this simple growth. Space stretches while light moves, increasing the distance between widely separated regions. Under some conditions, the separation grows so rapidly that light emitted now from a remote galaxy never reaches Earth, even if it travels forever through local space at the speed of light. This does not mean that the galaxy itself moves through space faster than light in the ordinary sense. General relativity allows the distance between faraway locations to increase faster than light because the intervening space expands. The local rule remains unchanged. Light always passes a nearby observer at the same measured speed. The larger separation grows because the geometry between distant regions changes. The distinction between motion through space and expansion of space is essential for understanding the horizon. Astronomers use several related horizons, each describing a different limit. The particle horizon marks the greatest present distance from which any signal could have reached Earth since the earliest stages of cosmic history. It defines the broad extent of the observable universe. The cosmic event horizon describes another boundary. It separates events that can ever influence Earth from events whose future signals will never arrive. A galaxy may remain visible today because ancient light from it is already traveling toward Earth, while light emitted by that same galaxy now may never be received. This delayed visibility gives the distant universe a layered appearance. Telescopes do not observe remote galaxies as they exist at the present cosmic time. They observe old images carried by light that began its journey long ago. Some galaxies currently seen in deep surveys may already lie beyond the event horizon in terms of signals emitted during their present era. Their ancient light remains available, but their later history becomes permanently hidden. Over immense time scales, more distant galaxies fade from view, as their light is stretched into wavelengths that become increasingly difficult to detect. The stretching of light is called cosmological redshift. As space expands, the wavelength of traveling radiation grows with it. Visible light shifts toward infrared wavelengths, then toward microwaves and radio waves. Its energy decreases, and its arrival becomes more widely spaced in time. A distant galaxy, therefore, appears dimmer, not only because of its great distance, but also because expansion weakens and slows the received signal. No sudden darkness marks the horizon. Instead, information becomes steadily older, redder, fainter, and less frequent. Current measurements indicate that cosmic expansion is accelerating. The cause is described in the standard cosmological model as dark energy, a name for the component associated with this accelerated growth. Its fundamental nature remains uncertain. If the present pattern continues, the event horizon remains a lasting feature. Regions beyond it continue to recede from causal contact. Gravity can hold nearby systems together, so galaxies within a bound group do not simply expand away from one another. On larger scales, however, unbound structures become increasingly isolated. The event horizon depends on the history of expansion, not merely on the present rate. Calculations trace how light paths behave as the scale of the universe changes. A signal may initially move toward Earth through changing surroundings, while distance still increases because space expands faster between the two locations. Later changing conditions may allow the distance to decrease or may prevent arrival forever. The outcome follows the geometry of space-time. The horizon is centered on the observer, but it is not unique to Earth. Every location has its own observable region and its own limits of causal contact. An observer in a distant galaxy sees a different sphere containing some regions visible from Earth and others hidden from it. Neither observer occupies a universal center. The horizon follows from the path available to signals reaching a particular place. It is therefore a boundary of observation and influence, not a fixed object embedded in the cosmos. There is no direct method for seeing what exists beyond the particle horizon. Scientific models usually assume that the large-scale properties measured within the observable region continue outside it because observations show broad uniformity across widely separated directions. This principle supports calculations, but it cannot turn inaccessible regions into measured facts. Matter may extend far beyond a horizon, perhaps across a universe much larger than the visible domain. Its exact distribution, total extent, and global form remain unknown. The horizon also places limits on experiments. No instrument can collect a signal that never arrives, regardless of its size or sensitivity. A larger telescope gathers more photons from accessible sources and resolves finer details, but it cannot cross a boundary established by causal structure. The limit is built into space-time itself. Physical theories may describe regions beyond it, yet those descriptions depend on assumptions tested only within the observable realm. At the widest distance, this separation unfolds without any visible edge. Galaxies do not strike a border or disappear at a single line. Their signals weaken as expansion lengthens the space they cross. The sky preserves their past while losing access to their future. Over time, the observable record becomes increasingly local, leaving gravitationally bound neighbors surrounded by growing darkness. The cosmic horizon remains silent and intangible, defining not where the universe stops, but where connection ends. At scales larger than individual galaxies and clusters, the universe forms a web of matter separated by regions where little is found. These regions are called cosmic voids. They are not empty, and they are not holes cut into space. They are volumes where the density of galaxies, gas, and dark matter falls below the cosmic average. Some extend across tens or even hundreds of millions of light years, creating expanses between the brighter filaments of the cosmic web. The structure begins with variations in the density of the early universe. These variations appear in the cosmic microwave background as differences in temperature. Regions containing a little more matter attract material through gravity. Over billions of years, dense areas grow into sheets, filaments, galaxy groups, and clusters. Less dense regions lose matter to their surroundings. As galaxies and gas move towards stronger concentrations, the underdense zones become wider and emptier. The resulting pattern resembles a three-dimensional network with voids occupying much of its volume. A cosmic void is identified by mapping the positions of many galaxies across a region of sky. Astronomers measure each galaxy's direction and redshift, then estimate its distance within an expanding universe. The survey produces a map showing crowded structures and sparse interiors. A void has no sharp wall. Galaxy density decreases gradually toward its center and rises toward surrounding filaments. Different methods define boundaries in different ways, but the pattern remains stable across major surveys. Inside a void, galaxies still exist. Many are small and isolated with fewer neighbors than galaxies in denser environments. Clouds of gas also pass through the region, and dark matter remains present at low density. The word emptiness, therefore, describes a relative condition. Compared with a cluster containing thousands of galaxies and hot gas, a void contains very little. Compared with a vacuum, it still holds matter radiation, magnetic fields, and particles moving through intergalactic space. Voids influence light traveling across them. Their low matter density produces weaker gravitational effects than the cosmic average. As light enters and leaves a changing gravitational region, its energy can shift slightly. This process contributes to subtle patterns in the cosmic microwave background. Voids bend light weakly through gravitational lensing. By measuring tiny distortions in the shapes of background galaxies, astronomers can estimate the amount of matter inside and around a void including dark matter that gives off no light. The largest voids grow as neighboring under-dense regions merge. Empty zones separated by walls can become part of a depression in matter density. Their expansion does not occur like an explosion from a central point. Matter flows outward because the surrounding regions exert stronger gravitational attraction. At the same time, cosmic expansion increases the distances between unbound locations. These effects allow void interiors to become rarefied, while their boundaries gather more structure. Galaxies near void edges trace curved walls and narrow strands. Their arrangement reveals how matter drains from emptier regions into denser ones. Computer simulations reproduce this behavior by following dark matter and ordinary matter from early conditions. When the initial density pattern matches observations, the simulated universe develops voids with sizes, shapes, and distributions similar to those in galaxy surveys. This agreement supports the picture of structure growing through gravity within an expanding cosmos. These measurements are difficult because the signal from a single void is small. Researchers often combine observations of many voids to detect an average effect. The results generally show a matter deficit surrounded by a denser ridge, although the exact profile depends on void size and definition. Observations indicate that ordinary galaxies trace the deeper distribution of dark matter only imperfectly. A region that appears nearly empty in a galaxy map may still contain a smooth background of unseen mass. Cosmic voids also provide tests of gravity and cosmic expansion. Their interiors are relatively simple because they contain fewer complex structures and less violent interaction than clusters. The motions of galaxies around voids respond to both gravity and the rate at which space expands. By comparing observed shapes and velocity patterns with theoretical predictions, astronomers examine whether the standard cosmological model remains consistent across large scales. Current evidence broadly supports that model, though measurement uncertainties remain significant. One large underdense region can attract attention when it appears aligned with an unusual patch in the cosmic microwave background. Such associations require caution. A void can contribute to a temperature variation, but known structures may not fully account for every observed anomaly. Statistical chance survey limitations and unrelated foreground effects can create apparent connections. Observations indicate that some large voids have measurable influence on background radiation, while it remains uncertain whether any single void explains the most prominent cold features. The darkness of a void is different from the darkness beyond a cosmic horizon. A void lies within the observable universe and can be studied through the objects around it, the faint galaxies inside it, and the way it affects passing light. Its emptiness is physical rather than causal. Signals cross it, telescopes map it, and particles move through it. Yet its scale makes it difficult to imagine. A beam of light may travel for millions of years while crossing a region containing very few luminous systems. Within these expanses, stars do not fill the sky in any familiar way. A planet inside a faint, void galaxy would still see its own stars and nearby companions, but beyond the local system, the surrounding cosmos would appear unusually sparse. Major clusters would lie far away, arranged along distant walls. The environment would remain governed by the same physical laws, though the distribution of matter would be quieter and thinner. Cosmic voids reveal that emptiness is one of the main architectural features of the universe. Most galaxies gather along boundaries, while most volume belongs to underdense regions. The visible cosmos is therefore not a uniform sea of stars. It is a network shaped by gravity expansion and ancient variations in density, with immense dark chambers occupying the spaces between luminous structures. Across the largest measurable distances, galaxies do not remain fixed relative to one another. Their separation increases as the universe expands. This expansion is not a movement away from a central point. It is a change in the scale of space itself, observed through the way distant light is stretched and through the changing relationships between large cosmic structures. For much of modern astronomy, researchers expect gravity to slow this expansion. Matter attracts matter, so a universe filled with galaxies, gas radiation, and dark matter appears likely to lose speed as it grows. The evidence changes near the end of the 20th century. Two research teams study distant exploding stars known as Type 1, a supernovae. These events occur when a white dwarf undergoes a thermonuclear disruption under conditions. Their peak brightness is not perfectly identical, but measurements allow astronomers to standardize them. Once their true luminosity is estimated, their apparent faintness reveals distance. Their spectra show redshift, which indicates how much the universe expands while their light travels toward Earth. The distant supernovae appear dimmer than expected in a universe whose expansion is slowing under gravity. After possible effects from dust, stellar evolution, calibration, and selection are examined, the measurements point toward a different history. Expansion slows during earlier cosmic eras, then begins to accelerate several billion years ago. Independent observations support this result. Patterns in the cosmic microwave background, the distribution of galaxies, and a preferred scale in the cosmic web all fit a model in which an additional component dominates the recent expansion. This component receives the name dark energy. The term does not describe a substance directly observed in a laboratory. It describes whatever produces the measured acceleration within the equations used to model the universe. In the standard cosmological model, dark energy accounts for most of the cosmic energy density. Dark matter supplies much of the remaining matter, while ordinary matter forms a smaller portion. The exact percentages depend on combined measurements and model assumptions, but the broad result remains consistent across surveys. The simplest explanation is the cosmological constant. In general relativity, empty space can possess a constant energy density. As the universe expands, matter becomes more diluted because the same material occupies a larger volume. Radiation thins and also loses energy as its wavelength stretches. A constant energy density does not dilute in the same way. It therefore becomes increasingly important as the universe grows. Once it dominates the overall dynamics, the expansion rate begins to accelerate. The cosmological constant fits current observations well, yet its physical meaning remains uncertain. Quantum theories suggest that empty space may contain vacuum energy, but estimates of its expected value differ enormously from the value inferred through cosmology. This mismatch is one of the deepest unresolved problems in theoretical physics. It may reflect incomplete understanding of gravity, quantum fields, or the way vacuum energy contributes to space-time. Observations establish the accelerated expansion, but they do not yet reveal the fundamental nature of its cause. Other possibilities remain under study. Dark energy may change with time instead of staying constant. A new field could fill space and evolve as the universe expands. Gravity itself might behave differently across distances, making acceleration an effect of incomplete gravitational theory rather than a separate component. These ideas must reproduce the success of general relativity within the solar system around stars and across galaxies, while also matching the history of cosmic structure. No alternative currently provides a clearly superior description of the full evidence. Astronomers test these possibilities by measuring expansion at different periods. Supernova surveys extend distance records across ranges of redshift. Galaxy maps reveal baryon acoustic oscillations, a preferred separation inherited from pressure waves in the early universe. Weak gravitational lensing traces how matter bends light and how structure grows. Galaxy clusters provide a record because their number and distribution depend on both expansion and gravity. Each method contains different uncertainties, so agreement among them strengthens the overall picture. Some measurements of the present expansion rate do not agree. Observations using nearby stars and supernovae often produce a higher value than estimates inferred from the early universe under the Standard Model. This difference is known as the Hubble tension. It may arise from unknown systematic effects, or it may indicate that the Standard Model lacks some physical ingredient. The significance changes as measurements improve, and no single explanation has gained general acceptance. The tension concerns the precise rate of expansion, while the evidence for acceleration remains supported. Acceleration does not pull apart every structure. Gravity and other forces hold bound systems together. Atoms do not expand with the universe. Planets do not drift away from their stars because of cosmic expansion. Galaxies and galaxy groups can remain bound when their internal gravity exceeds the effect of large-scale expansion. The acceleration becomes important mainly across vast distances between systems that are not gravitationally connected. If the cosmological constant remains unchanged, The long-term future follows a gradual pattern. Distant, unbound galaxies move farther away, their light becoming more red-shifted and faint. The space between separated regions grows while local bound structures continue their internal evolution. Star formation declines as usable gas is consumed, heated, or expelled. The expanding universe becomes colder and more dilute on average. This outcome is sometimes called heat death, though it describes a slow approach toward a state with little available energy for organized change rather than a sudden event. The future depends on the nature of dark energy. If its density changes, expansion may develop differently. Current measurements remain consistent with a constant value, but they allow a limited range of variation. Researchers therefore avoid treating the distant future as directly observed fact. It is a projection based on models that match present evidence. At this scale, the darkness grows through separation rather than destruction. Space expands between remote structures, carrying them beyond contact. The process unfolds without a center and without an outward edge as the geometry of the universe changes everywhere at once. Across the expanding universe, visible galaxies gather in long filament sheets and crowded knots. Between them lie the great voids, while around them extends a deeper framework that cannot be seen directly. This hidden framework is associated with dark matter, a form of matter inferred through gravity. It does not emit, absorb, or reflect detectable light in the ordinary way. The first clues appear inside galaxies. Stars near the outer edges of spiral galaxies move faster than expected if only visible matter supplies the gravity. Gas clouds also orbit at speeds that remain high, far from the bright central regions. According to ordinary gravitational calculations, these outer stars should move more slowly as distance from the galactic center increases. Instead, their measured speeds suggest that each galaxy is surrounded by a much larger halo of unseen mass. This halo extends beyond the luminous disk and contains more matter than the stars and gas that telescopes detect. Simulations show dark matter halos as elongated, irregular, and filled with smaller concentrations. Galaxies grow inside these halos as ordinary gas falls into their gravitational wells. The gas cools, condenses, and forms stars while the dark matter remains diffuse and invisible. The bright galaxy therefore occupies only the central part of a much larger structure. Its visible shape does not reveal the full extent of the mass controlling its surroundings. On larger scales, dark matter joins halos into the cosmic web. Early in cosmic history, small variations in density create regions with slightly stronger gravity. Dark matter responds to these differences without being slowed by pressure from light. It begins gathering into clumps while ordinary matter remains coupled to radiation for a longer period. After the universe cools and becomes transparent, ordinary gas falls toward the dark matter concentrations already forming. Over billions of years, this process produces galaxies, groups, clusters, filaments, and the boundaries around voids. Computer simulations follow this growth by beginning with density patterns consistent with the cosmic microwave background. Billions of model particles represent dark matter moving under gravity in expanding space. The particles gather into a network that closely resembles the structure mapped by galaxy surveys. When gas physics, star formation, radiation, and energetic events are added, luminous galaxies appear within the dark framework. The agreement does not prove every property of dark matter, but it shows that a cold, weakly interacting component explains many features of cosmic structure. The word cold describes the motion of dark matter in the early universe rather than its temperature in a familiar sense. Cold, dark matter moves slowly enough for small structures to form first. These structures merge into larger halos, creating a gradual hierarchy. Galaxies assemble inside growing concentrations, and clusters form where many filaments meet. A dark matter model made from rapidly moving particles would erase small density variations and produce a different pattern. Observed galaxies and clusters generally support the cold, dark matter picture. Galaxy clusters provide some of the strongest evidence for hidden mass. A cluster contains hundreds or thousands of galaxies along with vast clouds of extremely hot gas. The gas shines in X-rays and often contains more ordinary matter than all the cluster stars combined. Even this visible and detectable material cannot account for the gravity measured from galaxy motions or from the temperature of the gas. Much more mass is required to keep the cluster bound. Dark matter supplies the additional gravitational pull in the standard model. Light passing a galaxy cluster follows curved paths because mass bends space-time. This gravitational lensing can stretch background galaxies into arcs, produce multiple images, or create subtle distortions across a wide field. By measuring these effects, astronomers reconstruct maps of total mass without relying on the light emitted by the cluster itself. The resulting maps usually reveal broad concentrations extending beyond the visible galaxies and hot gas. They show the hidden web in outline, traced by the way it redirects light from more distant sources. Weak gravitational lensing extends this method across large regions of sky. The shapes of millions of background galaxies contain tiny statistical distortions caused by matter along their lines of sight. Individual galaxies have many natural shapes, so a single image provides little information. Large surveys combine enormous samples and search for shared patterns. These patterns reveal the distribution of matter between Earth and the distant sources. The maps show dense ridges, cluster halos, and lower density regions, creating a projected view of the cosmic web. Dark matter also influences how galaxies move toward one another. Groups and clusters grow as halos merge, pulling visible systems along with them. Streams of stars around galaxies can be disturbed by invisible substructures passing nearby. Small companion galaxies may be stripped as they orbit within larger halos. These effects help researchers test how smoothly dark matter is distributed and how many smaller clumps exist. No confirmed dark matter particle has yet been detected in a laboratory. Experiments search for rare interactions between dark matter and ordinary atoms deep underground, where rock shields detectors from many forms of radiation. Particle accelerators search for missing energy that could indicate new invisible particles. Astronomers also look for radiation produced if dark matter particles decay or destroy one another. So far, no result provides a widely accepted direct detection. The gravitational evidence remains strong while the microscopic identity remains unknown. Several alternatives attempt to explain the observations by changing the laws of gravity. Some modified gravity theories reproduce parts of galaxy rotation without dark matter but matching galaxy clusters. Gravitational lensing, the cosmic microwave background, and the growth of large-scale structure is more difficult. Current evidence broadly favors dark matter, although research continues because the absence of direct detection leaves an important gap. The invisible cosmic web therefore remains both mapped and unidentified. Its gravity shapes the locations of galaxies, guides gas into clusters, and preserves the memory of ancient density variations. Beneath it, unseen mass forms the larger architecture, extending through filaments and halos across the observable universe. Galaxy clusters are the largest gravitationally bound structures known, containing hundreds or thousands of galaxies, enormous clouds of hot gas, and far more unseen mass than visible matter. When two clusters approach one another, their combined gravity accelerates every component toward a violent encounter. The galaxy's gas and dark matter enter the collision together, but they do not respond in the same way. Their different behavior allows astronomers to separate the parts of a cluster and study matter that produces gravity without producing light. The galaxies inside each cluster are widely spaced compared with their individual sizes. During a cluster collision, most stars pass through the opposing system without striking anything. Entire galaxies move across one another like scattered points in a vast volume. Their paths bend under the changing gravitational field, but direct collisions between stars remain extremely rare. The galaxies therefore preserve much of their original motion as the two clusters cross. The hot gas behaves differently. It fills the space between galaxies and carries most of the ordinary matter in a cluster. Its temperature reaches tens of millions of degrees Celsius, so it emits strongly in X-rays. When gas from one cluster meets gas from another, the particles interact electromagnetically. Shock waves form, pressure rises, and the gas slows. Instead of passing freely through the collision, it becomes compressed and heated near the region of impact. Dark matter appears to behave more like the galaxies than the gas. Gravitational lensing maps show that most of the total mass continues forward with the galaxies while the bright X-ray gas remains behind. The separation is especially clear in a system known as the bullet cluster, where two clusters have already passed through each other. Optical observations locate the galaxies X-ray observations trace the hot gas, and lensing measurements reveal where most of the mass lies. The mass peaks do not match the brightest gas. They align more closely with the galaxies on opposite sides of the collision, since the gas contains most of the visible ordinary matter. Gravity, based only on ordinary matter, would be expected to concentrate near the gas. Instead, the strongest lensing signal follows regions where little ordinary mass is detected. The simplest interpretation is that dark matter passes through the collision with relatively little interaction, carrying most of the gravitational mass beyond the slowed gas. Lensing provides this evidence without requiring dark matter to shine. A cluster bends the light of more distant galaxies because its mass curves space-time. Strong lensing creates stretched arcs and repeated images near dense regions. Weak lensing produces smaller distortions across a broader area. Astronomers measure these patterns and reconstruct the projected mass distribution. The method includes all matter along the line of sight, whether luminous, hot, cold, or invisible. The bullet cluster is not the only example. Other merging clusters show offsets among galaxies' gas and lensing mass, although the geometry is not always as simple. Some collisions occur nearly along the line of sight, making separation difficult to see. Others involve several smaller groups, uneven gas clouds, or multiple passages. Each system provides a different arrangement of speed, angle, and time since collision. Researchers compare many examples because a single cluster can contain unusual features that complicate interpretation. These collisions also test how strongly dark matter interacts with itself. If dark matter particles collide, often a dark halo should experience drag as it passes through another halo. Its mass peak might lag behind the galaxies, spread outward, or remain closer to the gas. Observations generally show that dark matter crosses cluster collisions with little resistance. This places limits on the probability that dark matter particles scatter from one another, although the exact limits depend on models of cluster structure and collision history. A low interaction rate does not identify the particle. It only narrows the possibilities. Dark matter may still interact through forces too weak to produce a measurable offset. It may contain more than one component, or its behavior may depend on velocity and environment. Current cluster observations are consistent with matter that interacts mainly through gravity, but they do not reveal its mass, internal properties, or origin. Modified gravity theories face a demanding challenge in these systems. If the apparent missing mass arises only because gravity behaves differently, the strongest gravitational effect must still appear away from the region containing most ordinary matter. Some theories can reproduce parts of the lensing signal by adding fields or additional unseen components, but the separation remains difficult to explain without something that acts like extra mass. Cluster collisions therefore support dark matter as a physical component rather than only a correction to gravitational law. The gas itself records the violence of the encounter. X-ray images reveal shock fronts, compressed edges, and long wakes. Temperatures and densities change across these boundaries, allowing astronomers to estimate collision speeds. Early estimates for some systems produce extremely high values, but later simulations show that shock speed, gas speed, and cluster speed are not always identical. The geometry and gravitational environment must be modeled carefully. Over time, the separated components do not continue forever in straight lines. Gravity slows them, and the clusters may remain bound. They can move apart, turn and collide again before settling into a larger system. The gas gradually mixes and redistributes while galaxies orbit within the combined halo. The clearest offsets therefore last for a limited period. Observers see each cluster at one stage in a process unfolding across billions of years. The collision therefore exposes the cluster's hidden structure, separating components that normally overlap and appear as one gravitational system in space. In a merging cluster, invisible matter becomes visible through separation. The galaxies mark collisionless paths. The gas shows pressure and shock, and lensing traces the dominant mass. Their temporary displacement creates a natural experiment on a scale no laboratory can reproduce. Across millions of light years, gravity reveals a substance that remains unseen, passing through luminous matter with little sign of contact. Around every large galaxy extends a region far wider than its visible disk. This outer domain is called the galactic halo. It contains thin gas, scattered stars, globular clusters, streams of disrupted material, and a dominant concentration of dark matter. The halo has no sharp edge. Its density decreases gradually with distance, blending into intergalactic space while still influencing the motion of objects far beyond the bright spiral arms. The visible disk marks only a small fraction of the galaxy's full gravitational structure. Stars and gas in the disk orbit under the pull of all the enclosed mass. Near the outer edge, visible matter becomes sparse, yet orbital speeds often remain high. If gravity came only from stars and gas, the speed would fall with distance. Instead, measurements show that the unseen halo continues to add mass. The rotation curve stays nearly flat, revealing gravity where little light is present. Neutral hydrogen gas extends beyond many stellar disks and provides an especially useful tracer. Radio telescopes detect radiation from this cold gas, even where starlight is weak. Its motion outlines the outer rotation of the galaxy and shows how the gravitational field continues into darkness. In some systems, the gas disk bends or warps. Nearby companions' uneven accretion, magnetic effects, and the shape of the halo can all contribute. The pattern records a galaxy that remains active far outside its familiar luminous form. The halo itself is not perfectly smooth. Simulations based on cold, dark matter predict many smaller clumps orbiting within larger halos. Some clumps contain dwarf galaxies, while others may hold too little gas to form visible stars. These dark subhalos move through the outer galaxy and disturb nearby material through gravity. Their presence can be tested indirectly by studying narrow streams of stars' gravitational lensing and the motions of faint satellite galaxies. Stellar streams form when a dwarf galaxy or globular cluster passes repeatedly through the larger galaxy's gravitational field. Tidal forces pull more strongly on the side nearest the host galaxy than on the side farther away. Over time, stars escape from the smaller system and spread along its orbit. The result is a long, thin ribbon that can wrap around the galaxy for great distances. Each stream preserves information about the path of its former parent system and the gravity shaping that path. A smooth halo produces a relatively smooth stream. A passing dark clump can create a gap, a bend, or a change in density. Other processes can produce similar features, including encounters with visible clouds, spiral structure, or the central bar. So interpretation requires careful modeling. Researchers compare observed streams with many simulated histories. The aim is not to assign every irregularity to dark matter, but to determine whether the overall population of disturbances matches the expected number and mass of invisible subhalos. The outer halo also contains ancient globular clusters. These compact groups hold hundreds of thousands of old stars and orbit far above or below the disk. Their ages and chemical compositions preserve evidence of early galaxy assembly. Some form within the main galaxy, while others arrive through smaller galaxies that are later absorbed. Their present motions trace the combined gravitational field across regions where ordinary matter contributes little. Dwarf satellite galaxies offer another measure of hidden mass. Many are faint, with only a small number of stars spread across a large area. The speeds of those stars often imply much more mass than the stars themselves contain. Some satellites appear strongly dominated by dark matter. Their shapes and orbits also reveal tidal influence from the larger host. When a satellite passes close enough, stars can be stripped into streams while the remaining core gradually weakens. The number of observed satellites is smaller than the number of subhalos found in simple simulations, though the difference has narrowed as faint systems are discovered and models of star formation improve. Many small halos may never gather enough gas to produce stars, especially after early radiation heats and removes their material. Observations indicate that dark structures may be far more numerous than luminous dwarf galaxies, while the exact abundance remains uncertain. Hot gas fills much of the halo around large galaxies. It reaches temperatures of hundreds of thousands or millions of degrees Celsius and emits weakly in ultraviolet and X-ray wavelengths. Some of this gas arrives from intergalactic space. Some is expelled from the disk by stellar winds and supernova explosions. It can remain suspended for long periods before cooling and returning. This circulation links the visible galaxy with its extended surroundings and controls how much material remains available for future star formation. The halo contains metals, meaning elements heavier than helium carried outward by generations of stars. Their presence shows that galactic material travels far from the disk. Absorption lines in the spectra of distant background sources reveal these thin clouds when their light passes through the halo. A single line of sight detects only a narrow column, so many observations are combined to map the larger environment. Magnetic fields and energetic particles also extend into the halo. They are difficult to measure because signals are faint and mixed with foreground emission. Their strength, structure, and origin remain areas of active study. They may influence how gas moves, cools, and returns to the disk, though gravity remains the main force shaping the halo on the largest scales. Across these outer distances, every measured orbit becomes a quiet record of mass that remains present without revealing its own light. The darkness inside a galaxy is therefore not an empty margin around a visible disk. It is a broad, structured environment containing the greater part of the galaxy's mass. Streams, satellites, gas clusters, and faint stars move through it, each responding to the same invisible gravitational field. The luminous disk appears as one concentrated layer within a far larger system whose boundaries remain diffuse, whose contents are only partly known, and whose hidden architecture governs the slow motion of matter across the galactic outskirts. At the center of the Milky Way, the disk narrows into a crowded region filled with stars, dense gas dust clouds, and strong gravity. Earth lies about 26,000 light-years away, viewing this region through the disk. Dust blocks most visible light, so the region appears dark to telescopes. Infrared radio and X-ray instruments reveal the hidden structure by detecting wavelengths that pass through the dust or emerge from hot material. The central few light-years contain the compact nuclear star cluster. Millions of stars occupy a volume far denser than the neighborhood around the Sun. Many are faint, while some are young, massive, and luminous. Their orbits cross in many directions rather than following the orderly rotation of the galactic disk. Gravity dominates every motion, creating a complex swarm around an unseen central mass. At the dynamical center lies Sagittarius, a star, a radio source associated with a supermassive black hole. The black hole contains about 4 million times the mass of the Sun. Its presence is established through the motion of nearby stars. These stars trace elongated paths around a point that emits little visible light. One star completes an orbit in roughly 16 years, passing close to the central object at tremendous speed. Its path follows the predictions of gravity around a compact mass. Repeated measurements map these stellar orbits precisely. Infrared telescopes separate individual stars despite the crowded field and extinction. As each star moves, astronomers record changes in position and speed. The data show that millions of solar masses occupy a region far smaller than the solar system. No stable cluster of ordinary dark objects can remain so compact without collapsing or dispersing. A supermassive black hole provides the simplest explanation consistent with the evidence. The black hole remains invisible because light cannot escape from within its event horizon. However, gas outside the horizon emits radiation as it heats, accelerates, and interacts with magnetic fields. Sagittarius. A star is faint compared with active galactic nuclei in other galaxies. It consumes matter slowly despite being surrounded by stars and gas. Most nearby material does not fall directly inward. It circulates, collides, heats, and escapes, while only a small fraction reaches the innermost region. Radio observations reveal changing emission from hot plasma close to the black hole. Infrared and X-ray flares sometimes appear lasting minutes to hours. These events may arise when magnetic fields reconnect or when heated gas moves through the inner flow. Observations identify rapid changes but do not reveal all plasma details. The environment is small on galactic scales, yet it remains difficult to resolve because of its distance and scattering by material between Earth and the center. A network of radio observatories combines signals from across Earth to form a virtual telescope as wide as Earth. This method, called very long baseline interferometry, resolves the black hole's immediate surroundings. Images of Sagittarius A star show a ring-like structure around a darker central region. The pattern is consistent with glowing plasma bent by intense gravity around the black hole. The dark center is called a shadow, created by captured light paths and strong gravitational lensing. The observed ring does not represent the event horizon as a solid surface. It comes from radiation traveling through curved space-time around the black hole. Some light circles partway around before escaping toward Earth, while other paths end at the horizon. The size of the shadow agrees with the mass estimated from stellar orbits. This connection brings together measurements made across very different scales, from years of stellar motion to radio signals formed near the boundary of the black hole. The central black hole also influences nearby gas clouds and stellar winds. Massive young stars release material at high speed, filling the region with hot, thin gas. Collisions among these winds create X-ray emission. Some gas loses angular momentum and moves inward, but much is pushed outward or remains in unstable circulation. The feeding process is therefore irregular. The black hole's low brightness suggests that most available material never reaches the point where it can release large amounts of energy. Farther from the center, dense molecular clouds form a twisted ring of cold gas and dust. This central molecular zone contains regions of intense pressure, turbulence, and magnetic activity. It holds enough material for star formation, yet its star formation rate is lower than simple estimates might predict. Strong turbulence, tidal forces, temperature, and magnetic fields may slow the collapse of clouds. Observations indicate that stars still form in selected pockets, while much of the gas remains unsettled. The galactic center also produces extended radio and X-ray structures. Filaments trace magnetic fields through the region, and larger lobes rise above and below the plane. Some features may record past activity from the central black hole, while others may result from concentrated star formation and supernova explosions. Their exact origins remain uncertain because several processes operate in the same crowded environment. The present quiet state does not mean the center has always remained faint. Despite its density, the galactic center is not filled with frequent stellar collisions. Stars are still small compared with the distances separating them. Close gravitational encounters occur more often than near the Sun, gradually changing orbits and redistributing energy. Compact remnants such as white dwarfs, neutron stars, and stellar black holes are expected to gather toward the center through repeated interactions. Their exact numbers are difficult to measure because most remain faint. Within this central region, darkness comes from both dust and gravity. Dust hides the crowded stars from visible sight, while the black hole hides its own interior from every wavelength. The surrounding motions reveal what cannot be seen directly. Stars sweep around. An empty point, hot plasma, flickers near the central boundary, and radio waves outline light bent into a ring. The quiet center remains active in subtle ways, governed by a mass that is measured through every orbit, but observed only through its effect on nearby matter. Near the centers of many galaxies, a black hole rests within a field of stars. Most stars remain on orbits and pass through the region without approaching the boundary. A small number move along paths that carry them close. When one of these stars enters the black hole's tidal influence, gravity no longer pulls evenly across its body. The near side feels a stronger attraction than the far side, and the difference begins to distort the star. This difference in gravitational pull is called a tidal force. The same effect raises tides on Earth, although the scale near a black hole is greater. A star is held together by its own gravity and by pressure generated in its interior. As it approaches the black hole, the tidal force grows. If the star crosses a critical distance known as the tidal radius, the black hole's uneven pull becomes stronger than the star's ability to remain intact. The star stretches along the direction of the black hole and compresses across the other directions. Its spherical shape becomes elongated. Gas layers begin to separate, and the ordered structure of the star breaks apart. This process is sometimes described as spaghettification. Though the physical event is governed by gravity rather than by any material surface, it is dismantled into a stream of plasma along paths. The location of the tidal radius depends on the mass of the black hole and the size and density of the star. A larger star is more easily disrupted than a compact one. A dense white dwarf can survive closer to a black hole than a normal star before being torn apart. Around the most massive black holes, the event horizon may lie outside the tidal radius for ordinary stars. In that case, a star can cross the horizon before visible disruption occurs, leaving little external signal. When disruption happens outside the horizon, roughly half of the stellar debris often gains enough orbital energy to escape. The rest remains gravitationally bound to the black hole. The escaping material forms a thin stream that travels outward into the galactic center. The bound material follows elongated orbits and later returns toward the point of closest approach. The first returning debris is the most tightly bound and completes its path sooner than the rest. As the stream returns, parts of it can collide. General relativity causes the orbit to shift slightly with each passage, preventing the debris from following exactly the same path. Collisions convert orbital motion into heat. The gas begins to circularize gradually, forming a rotating flow around the black hole. This process may be rapid in some events and inefficient in others. Observations indicate that the shape, viewing angle, magnetic fields, and black hole spin can all affect how the debris settles. The heated material emits intense radiation. Much of the energy appears in ultraviolet and X-ray wavelengths, though some events shine strongly in visible light. A previously quiet galactic nucleus can brighten dramatically over weeks or months. The radiation then fades as the supply of returning debris decreases. The decline does not always follow a simple pattern because the conversion of falling matter into light depends on the structure of the flow. Astronomers identify these events by monitoring large areas of sky and searching for temporary sources near galactic centers. A sudden flare must be distinguished from a supernova, an active galactic nucleus, or another variable object. Its location, color temperature, spectral lines, and evolution provide clues. Tidal disruption events often remain hot as they fade, unlike many supernovae, which cool more steadily as expanding debris loses energy. Spectra reveal broad emission lines from hydrogen, helium, or both. These lines form in rapidly moving gas, illuminated by the central flare. Their shapes can change as the debris expands, collides, and reorganizes. Some events show strong X-rays, while others are weak at high energies despite bright optical emission. Dust surrounding the nucleus can absorb short wavelength radiation and re-radiate the energy in infrared light, producing a delayed echo. Radio emission appears in a smaller group of events. It can arise when outflowing material strikes gas around the black hole. In rare cases, the disruption launches a narrow relativistic jet, a stream of particles moving close to the speed of light. When such a jet points near Earth, its radiation becomes strongly enhanced. These events are unusually bright, but they do not represent the typical tidal disruption. Most observed cases show slower winds or weaker outflows. The black hole gains only part of the star's mass. Radiation winds and escaping debris remove a significant fraction. Material that reaches the inner flow releases gravitational energy before crossing the horizon. This energy powers the flare. The event, therefore, makes a normally dark black hole temporarily visible through the destruction occurring outside it, not through light emerging from within. Tidal disruption events occur rarely in any single galaxy. Perhaps once every tens of thousands or hundreds of thousands of years, though estimates remain uncertain. Large surveys observe many galaxies at once, allowing rare flares to be found. Their rates depend on how stars move through crowded galactic centers, how often gravitational encounters alter their orbits, and whether more than one black hole is present. These events provide measurements of black holes that are otherwise inactive. The flare's temperature, duration, luminosity, and spectral evolution constrain the black hole's mass and the behavior of matter in strong gravity. At the same time, each event remains difficult to interpret completely. The star's structure is unknown, the debris flow cannot be directly resolved, and several physical processes overlap. A tidal disruption ends with most of the visible light fading into the background of the host galaxy. Escaping stellar gas continues outward, while bound material either falls inward or remains in orbit. The black hole returns to a quieter state. Only a changed environment and a diminishing stream of radiation remain, marking the place where a star once crossed too deeply into an uneven gravitational field. Between the stars, planets may travel without belonging to any solar system. These objects are called rogue planets or unbound planets. They move through the galaxy under the gravity of stars, gas-dark matter, and the Milky Way itself. Unlike planets that circle a parent star, they receive no daylight and no regular supply of stellar warmth. Their surfaces and atmospheres develop in an environment shaped mainly by internal heat, background radiation, and encounters with other objects. Some rogue planets may form in the same way as ordinary planets. Inside a young planetary system, several growing worlds can pull strongly on one another. Their orbits change through repeated gravitational encounters. A close passage between large planets can transfer enough energy to send one body outward. If its speed becomes greater than the escape speed of the system, it leaves the star permanently. The remaining planets settle into new orbits, while the expelled world begins an independent path through interstellar space. Other objects may form more like stars. A cold cloud of gas can collapse under gravity and produce an object too small to sustain ordinary hydrogen fusion. Brown dwarfs occupy part of this range, but the boundary between a very small brown dwarf and a very large rogue planet depends partly on formation history. Observations indicate that isolated planetary mass bodies exist, while their origins remain uncertain in many cases. Rogue planets are difficult to detect because they emit little visible light. Young examples retain heat from formation and glow weakly in infrared wavelengths. Telescopes can find some of these objects in nearby star-forming regions where their ages and distances are estimated from the surrounding population. Older rogue planets cool steadily and become much fainter. A world similar in mass to Earth may be almost impossible to see directly across interstellar distances. Gravitational microlensing provides another method. When a rogue planet passes close to the line of sight between Earth and a distant star, its gravity bends, and magnifies the star's light. The background star briefly brightens even though the planet itself remains dark. The duration and shape of the brightening depend on the lens mass, speed, and geometry. A planetary mass object can produce an event lasting from hours to days. Micro-lensing events do not usually repeat because the alignment is temporary. Astronomers therefore monitor millions of stars in crowded regions toward the center of the Milky Way. Automated surveys search for small changes in brightness and compare them with the smooth pattern expected from gravitational lensing. Weather variable stars, detector errors, and blended sources complicate the measurements. Space telescopes can provide steadier observations and different viewing angles, improving estimates of the lensing object's mass. Early studies suggest that rogue planets may be common, but estimates vary widely. Some analyses find large populations of objects with masses near Jupiter, while later work places lower limits on their abundance. Earth mass rogue planets may also exist in significant numbers, though they remain hard to measure. Current evidence supports a substantial population of unbound worlds, but the total number per star is not firmly known. Without a star, a rogue planet does not necessarily become completely frozen throughout. A giant planet can retain heat from slow gravitational contraction and from the settling of material inside it. Radioactive elements in rocky planets also release energy over long periods. A thick atmosphere can trap part of this heat. Hydrogen in particular can provide strong insulation at high pressure. Under certain conditions, a planet far from any star may preserve liquid water beneath ice, or even beneath a dense atmosphere. A frozen surface can shield deeper layers from the cold of space. If geothermal heat rises from a rocky interior, an ocean may remain liquid below many kilometers of ice. The required conditions depend on the planet's mass composition, age, and radioactive inventory. Such hidden oceans are physically possible, but no confirmed example has been observed on a rogue planet. Their existence remains a prediction based on planetary models. Large moons could remain bound to an ejected giant planet. The planet and moons would leave their original system together if the encounter does not disrupt the satellite orbits. Tidal forces between a moon and planet can generate heat within the moon, especially if its orbit remains eccentric. This process could maintain subsurface liquid in some cases. The system would still travel through darkness with only faint infrared emission and occasional auroral light. An atmosphere on a rogue planet evolves without stellar radiation. There is no ordinary day and night cycle, though weather can still arise from internal heat and rotation. Clouds may form from water, ammonia, methane, or other compounds depending on temperature. Winds distribute energy through the atmosphere. On very cold worlds, gases that remain airborne on Earth can freeze and fall onto the surface. A thick hydrogen atmosphere may remain gaseous because hydrogen condenses only at extremely low temperatures. The sky above such a planet would not be entirely black. Stars would still cover the surrounding galaxy, though none would dominate as a nearby sun. The Milky Way might form a broad band of light altered by the planet's position among dust clouds and stellar populations. Without a bright daytime sky, distant stars could remain visible continuously above clear regions. Any aurora, lightning, volcanic glow, or artificial light would appear against permanent darkness. Rogue planets can pass near stars, but direct capture is unlikely unless another body removes orbital energy. A planet may cross a planetary system and disturb comets or planets before continuing outward. Very close encounters are rare because interstellar distances are vast. Most rogue worlds move for billions of years without approaching another star closely. Their final paths follow the slow circulation of the galaxy. Some remain within the Milky Way, orbiting its center among the stars. Others may gain enough speed to escape into intergalactic space. They are worlds without sunrise, carrying ancient heat and possible buried oceans through regions where light arrives only from distant stars. Across deep space, some of the brightest brief events in the observable universe appear as gamma-ray bursts. They arrive without warning from distant galaxies and release most of their detectable energy. In gamma rays, the highest energy form of electromagnetic radiation. A burst may last less than a second or continue for several minutes. During that short interval, it can outshine the combined gamma-ray emission of every other source in the sky. The first detections occur through satellites built for another purpose. Instruments searching for nuclear tests record flashes that do not come from Earth. Later missions show that the bursts arrive from all directions with no concentration toward the plane of the Milky Way. This distribution suggests a distant origin. Precise positions eventually connect fading afterglows with remote galaxies, confirming that the explosions occur across cosmological distances. Gamma-ray bursts fall broadly into two groups based on duration and other properties. Long bursts usually last more than a few seconds and are linked to the collapse of massive stars. Short bursts generally last less than about 2 seconds and are associated with mergers involving neutron stars. The boundary is useful but not absolute. Some events do not fit neatly into either class, and duration alone cannot reveal every physical detail. A long burst begins in the core of a very massive star after nuclear fuel can no longer support it. The core collapses under gravity and forms a black hole, or in some cases a rapidly rotating neutron star with an intense magnetic field. Material from the surrounding star falls inward and forms a hot disk. Under suitable conditions, the central system launches narrow jets along its rotation axis. These jets move outward at speeds close to the speed of light. They contain particles, radiation, and magnetic fields moving with extreme energy. As the jets force their way through the collapsing star, they create shocks and channels in the stellar material. If a jet reaches the surface and points near Earth, satellites can detect the gamma-ray burst. If the jet points elsewhere, the same explosion may appear only as an unusual supernova or remain difficult to recognize. The gamma rays probably form within the jet through processes involving shocks, magnetic fields, and rapidly moving particles. Electrons accelerated to high energies can emit radiation as they spiral through magnetic fields. Collisions within the outflow may also convert motion into heat and light. Observations support several mechanisms, but it remains uncertain which process dominates in every burst. The internal structure of the jet cannot be directly imaged at the moment of emission. After the first flash, a longer afterglow develops across X-ray, ultraviolet visible infrared, and radio wavelengths. The jet collides with gas around the explosion and drives a shock into the surrounding medium. Particles accelerated at the shock produce radiation that fades over hours, days, months, or longer. By following this decline, astronomers estimate the jet energy density of nearby gas and geometry of the outflow. A break in the fading pattern can reveal the narrowness of the jet. Early in the event, relativistic motion concentrates radiation into a small forward direction. As the jet slows, a wider portion becomes visible. When its edge enters view, the afterglow may dim more rapidly. This change helps researchers correct the apparent energy for beaming. The true energy is lower than it would be if the burst radiated equally in every direction, though it remains enormous. Short gamma-ray bursts arise through a different path. Two neutron stars orbit one another, losing energy through gravitational waves and moving gradually closer. Their final merger disrupts the stars and creates a black hole or a heavier neutron star. A compact disk of debris forms around the remnant and a narrow jet may emerge. The event also ejects neutron-rich matter that produces heavy elements through rapid nuclear reactions. A nearby merger observed through both gravitational waves and light confirms this connection. The gamma-ray signal is weaker than many distant short bursts, likely because the jet does not point directly toward Earth. Its later radio and X-ray emission rises and falls in a way consistent with a structured jet viewed from the side. The event demonstrates that a single collision can send information through space-time vibrations and electromagnetic radiation. Gamma-ray bursts can affect matter across large distances. Their radiation ionizes gas near the source and may alter the atmospheres of planets within a sufficiently close region. In the Milky Way, a nearby burst directed toward Earth could damage atmospheric chemistry. Such an event is possible but rare. No evidence shows that a gamma-ray burst currently threatens Earth, and estimates of past biological effects remain uncertain. Most bursts occur so far away that their radiation reaches Earth as a faint signal detectable only by sensitive instruments. Satellites identify the initial flash and rapidly transmit its position. Telescopes around the world then search for the afterglow. Speed matters because the source fades quickly. Coordinated observations combine wavelengths and reveal changes that no single instrument can follow alone. Some bursts appear from eras when the universe is less than 1 billion years old. Their bright afterglows pass through ancient gas and carry information about early galaxies, chemical enrichment, and the growing intergalactic medium. The explosion itself lasts briefly, but its light crosses billions of years before reaching detectors. A short flash, therefore, becomes a record of both stellar death and the long space between galaxies. Because Earth detects only jets aimed close to its line of sight, the observed population represents a small fraction of all such explosions. Many similar stellar collapses and mergers remain unseen as gamma-ray sources. The darkness returns after each burst. Gamma rays vanish first, followed by fading X-rays, visible light, and radio emission. Expanding debris merges with its surroundings while the compact remnant remains hidden. Across deep space, the event leaves only altered gas, newly formed elements, and radiation traveling outward through the universe. Massive stars spend their lives balancing two opposing forces. Gravity pulls every layer inward while pressure from hot gas and radiation pushes outward. This balance is called hydrostatic equilibrium. It remains stable only while nuclear reactions in the core continue to release enough energy. A massive star, therefore, survives through a sequence of fuels, each producing the heat required to resist collapse for another stage of its life. Hydrogen fuses into helium during the longest period. When hydrogen becomes scarce in the core, the central region contracts and grows hotter. Helium then fuses into carbon and oxygen. In stars with enough mass, later stages create heavier elements through increasingly brief periods of fusion. Carbon, neon, oxygen, and silicon become fuels in turn. Each stage releases less useful energy and lasts for a shorter time than the one before it. The interior develops into layers of different composition. Lighter elements remain farther from the center, while heavier products collect within. The structure is often compared with nested shells, though the boundaries are active and uneven. Convection carries heat and material through some regions. Burning shells shrink, and interact. The star loses mass through winds, and its outer appearance may change greatly, yet the central core continues moving toward a limit imposed by nuclear physics. Silicon fusion produces elements near iron. Iron is important because joining iron nuclei does not release energy in the way earlier fusion reactions do. Splitting iron also requires energy. Once an iron-rich core forms, the star no longer has another ordinary fusion stage capable of supporting it. The core grows as surrounding shells continue to add material. Its pressure depends mainly on electrons packed so closely that quantum rules resist further compression. This electron pressure can support only a limited mass. As the core approaches that limit, rising temperature and density trigger processes that remove support. High-energy photons break iron nuclei into lighter particles, consuming energy that had helped maintain pressure. Electrons are forced into protons, producing neutrons and neutrinos. The number of free electrons falls, so electron pressure weakens. The core then loses stability and begins a rapid gravitational collapse. The collapse lasts only a fraction of a second. Matter falls inward at thousands of kilometers per second. The central density rises from values typical of white dwarf matter toward densities found inside atomic nuclei. Neutrinos are produced in enormous numbers. At first, they escape, but as density increases, they scatter repeatedly and become temporarily trapped. The inner core contracts more slowly as nuclear forces and the resistance of densely packed particles become important. Infalling material continues toward the center and strikes the stiffened inner core. The sudden deceleration produces a pressure wave that moves outward as a shock. Early models suggest that this shock alone might explode the star, but calculations show that it quickly loses energy. It breaks apart heavy nuclei and creates more neutrinos. The shock stalls within the collapsing star while fresh material continues to fall through it. Neutrinos help revive the stalled shock. Some of the immense neutrino flow deposits energy behind the shock, heating the surrounding matter. Turbulent motion, convection, rotation, and asymmetric flows can increase the time available for this heating. Under suitable conditions, the shock begins moving outward again. It crosses the star, ejecting the outer layers in a core collapse supernova. The exact mechanism is complex, and simulations continue to improve, but neutrino heating is central to the standard explanation. The explosion does not resemble a smooth expanding sphere. Instabilities create plumes, knots, and uneven distributions of elements. Material from deep layers can mix outward while hydrogen and helium move inward through turbulent flows. The shock heats the stellar envelope and drives it into space. Radioactive nuclei form during the event, decay, and provide energy that keeps the expanding debris bright. After the first shock, energy begins to fade. The light curve records this changing energy supply. Some supernovae remain bright for a plateau because a large hydrogen envelope slowly releases stored heat. Others decline more quickly after losing much of their outer gas before collapse. Spectra reveal the elements present and their speeds. Hydrogen lines, helium lines, or the absence of both, allow astronomers to classify different explosions. These categories reflect variations in mass loss, binary interaction, composition, and structure before collapse. A massive star often evolves with a companion. Matter can flow from one star to the other, removing the outer envelope or changing the core mass. Two stars may merge before the final collapse. These interactions explain why stars born with similar masses can produce very different supernovae. The final outcome depends not only on initial mass, but also on rotation, metallicity winds, and the history of the binary system. The compact remnant at the center receives a sudden recoil when the explosion is asymmetric. It may move through space at hundreds of kilometers per second. If enough matter falls back after the explosion, the remnant gains mass. In some cases, the explosion remains weak and much of the star collapses inward, producing a black hole with little visible display. Observations indicate that some massive stars may disappear in this way, though the frequency remains uncertain. The expelled debris expands for thousands of years and forms a supernova remnant. Its shock sweeps through surrounding gas, heating it to temperatures that produce X-rays. Electrons moving through magnetic fields generate radio emission. Optical filaments mark cooling gas and dense clumps. Newly made elements spread into interstellar space where they later become part of clouds, stars, planets, and dust. The death of a massive star is therefore both collapse and dispersal. Gravity compresses the core into a compact object, while the explosion releases the outer layers into the galaxy. The star's long sequence of nuclear burning ends in seconds of rapid change. What remains is a dense central remnant surrounded by an expanding field of heated gas, radioactive material, and heavy elements carried into the darkness between stars across many future stellar generations. A neutron star forms when the collapsed core of a massive star survives without becoming a black hole. It contains more mass than the Sun packed into a sphere only about 20 kilometers across. The compression is so extreme that atoms cannot remain in their ordinary form. Electrons combine with protons, producing neutrons and neutrinos, while gravity forces matter into densities comparable with those found inside atomic nuclei. The surface is not a familiar, solid boundary. It consists of tightly packed nuclei and electrons arranged under enormous pressure. Beneath it, density rises rapidly. The outer crust contains nuclei in a lattice surrounded by free electrons. Deeper layers contain nuclei with increasing numbers of neutrons. At still greater density, some neutrons move outside the nuclei and form a fluid through the crust. The exact composition changes with pressure, and several details remain uncertain because laboratory experiments cannot reproduce the same conditions across such large volumes. A neutron star supports itself through quantum effects and the strong nuclear force. Neutrons resist being placed into identical states, creating pressure even without ordinary heat. Interactions among particles add further support. Gravity remains so powerful that the star's structure depends on general relativity. The maximum mass that this support can hold is not known precisely. Observations indicate that neutron stars can exceed twice the mass of the Sun, while objects above a higher uncertain limit collapse into black holes. The star is born hot, with temperatures reaching hundreds of billions of degrees Celsius in its interior. Neutrinos carry away much of this heat during the first moments. The surface cools more slowly, radiating X-rays for thousands or millions of years. Cooling rates depend on the particles and reactions inside. Some neutron stars cool faster than others, suggesting differences in mass composition, superfluid behavior, or magnetic field. Measurements provide clues, but no single cooling path describes every object. Many neutron stars rotate rapidly because the collapsing core preserves angular momentum. A large star turns slowly, but when its core contracts into a much smaller sphere, the rotation speeds up. Some newborn neutron stars rotate several times each second. Older neutron stars in binary systems can spin hundreds of times each second after gaining matter from a companion. The fastest known examples complete a rotation in only a few thousandths of a second. A rotating neutron star with a magnetic field can produce beams of radiation from regions near its magnetic poles. If a beam sweeps across Earth, instruments detect regular pulses. The object is then called a pulsar. Radio pulses may arrive with remarkable stability, allowing astronomers to measure tiny changes in rotation. Pulsars gradually lose energy and spin more slowly, though sudden jumps called glitches sometimes interrupt the steady decline. Glitches may result from interactions between the crust and a superfluid inside the star. A superfluid moves with almost no internal friction and can store angular momentum in rotating vortices. As the crust slows, the interior fluid may remain partly separated. When vortices shift or release their stored motion, angular momentum transfers to the crust and briefly increases the observed spin. This explanation matches many features, though the detailed behavior of the interior remains under study. The magnetic fields of ordinary pulsars are already enormous compared with planetary or stellar fields. Some neutron stars possess fields hundreds or thousands of times stronger. These objects are called magnetars. Their magnetic energy powers bursts of X-rays and gamma rays along with persistent high-energy emission. The field may twist the crust, drive electric currents through the magnetosphere and stress the solid outer layers until they fracture or shift. A magnetar burst can last only a fraction of a second, while larger outbursts continue through repeated flashes and enhanced emission. Rare giant flares release far more energy. Their initial spike may be followed by a pulsing tail shaped by the star's rotation. Even these events do not involve the destruction of the neutron star. They represent a sudden rearrangement of magnetic fields and crustal stress within an object that remains gravitationally intact. The crust is strong because matter is compressed into a dense lattice. Yet the magnetic field can impose forces beyond ordinary experience. When the crust yields, seismic waves may travel through the star. These vibrations can affect the surrounding magnetic field and produce changing brightness. Researchers search flare signals for repeated frequencies that might reveal the star's internal structure, though identifying these patterns remains difficult. Magnetars also slow their rotation rapidly because their strong fields carry energy away. Most rotate once every few seconds, slower than many radio pulsars, despite being young. Some emit radio pulses after X-ray outbursts, while others remain radio quiet. The distinction between pulsars and magnetars is therefore not absolute. Neutron stars occupy a broad range of magnetic fields, ages, rotation rates, and emission states. Binary systems reveal another side of neutron star behavior. Gas from a companion can fall toward the star and form an accretion disk. As matter descends through the gravitational field, it heats to millions of degrees Celsius and emits X-rays. Magnetic fields guide part of the flow toward the poles, creating bright regions that rotate with the star. Accretion can also transfer angular momentum and spin the neutron star faster. The gravity at the surface is immense. Light loses energy as it climbs away, producing gravitational redshift. The path of light also bends, allowing an observer to see more than half of the surface at once. Matter falling onto the star releases far more energy per unit mass than matter falling onto an ordinary star. A layer only a few centimeters thick can contain extraordinary pressure. Neutron stars, therefore, remain compact laboratories for matter gravity, rotation, and magnetism. Their pulses mark stable clocks, their glitches expose hidden motion, and their flares reveal magnetic stress. Each signal comes from a sphere smaller than a city, carrying a stellar mass within darkness. Its quiet surface conceals layers that remain inaccessible to any direct physical measurement. A black hole is defined by a boundary called the event horizon. This boundary is not a material surface. It marks the region from which no signal can return to the universe. Light particles and all information remain trapped once they cross it. The horizon, therefore, separates events that can still influence distant observers from events that remain permanently hidden. For a non-rotating black hole, the size of the event horizon depends on mass. A black hole with several times the mass of the Sun has a horizon only tens of kilometers across. A supermassive black hole contains millions or billions of solar masses and possesses a horizon spanning millions or billions of kilometers. The boundary grows with mass, while the average density enclosed within it can become lower for larger black holes. Gravity near the horizon is described by general relativity. Matter does not encounter an invisible wall as it falls inward. Instead, space-time is curved so strongly that every future path inside the horizon leads toward the central region. Outside the horizon, light can still escape if it travels along a suitable direction. At the horizon, the outward path remains fixed at the boundary. Inside, even outward directed light moves deeper inward because the geometry allows no route back. A distant observer never sees an object cross the horizon directly. Light emitted from the falling object becomes increasingly red-shifted and delayed. Each later signal arrives weaker and at a longer wavelength. The object appears to slow fade and approach the boundary without visibly passing through it. This appearance comes from the behavior of light near the horizon, not from the experience of the falling object. For matter falling freely into a sufficiently large black hole, crossing the horizon may produce no sudden local event. The surrounding gravitational field changes smoothly at the boundary. An observer traveling with the material passes inward after a finite amount of proper time. Communication with the outside then becomes impossible. Signals sent after crossing cannot reach distant space regardless of the power used to transmit them. Tidal forces depend strongly on black hole mass. Near a small stellar black hole, the difference in gravity across an object can become destructive before the horizon is reached. Near a supermassive black hole, the horizon lies farther from the central region and tidal forces there can be weaker. Matter may cross the boundary before being stretched severely. The later evolution remains hidden because no information returns. Most detected black holes reveal themselves through material outside the horizon. Gas approaching a black hole usually carries angular momentum, so it does not fall directly inward. It forms a rotating accretion disk. Friction, turbulence, and magnetic stresses move angular momentum outward, allowing some gas to spiral inward. Gravitational energy becomes heat, and the inner disk can reach temperatures that produce ultraviolet light or X-rays. The disk remains outside the horizon. Its inner edge depends on the black hole's mass and rotation. Stable circular orbits end at a region called the innermost stable circular orbit. Matter moving inside this limit plunges inward rapidly. A rotating black hole drags nearby space-time around with it, changing the location of stable orbits and affecting the energy released by falling gas. Magnetic fields threading the disk can become twisted and amplified. They guide hot plasma launch winds and sometimes help produce narrow jets moving away from the black hole's poles. These jets do not emerge from inside the event horizon. They form in the surrounding region, drawing energy from the rotating disk and possibly from the black hole's spin. The exact launching process remains an active area of research. A black hole may also possess a region outside the horizon called the ergosphere when it rotates. Within this region, space-time itself is dragged so strongly that no object can remain stationary relative to distant space. Matter and light can still escape from the ergosphere if they follow suitable paths. The region, therefore, differs from the event horizon, although both arise from the geometry around a rotating mass. Observations cannot image the horizon directly as a physical surface. Radio telescopes instead detect glowing plasma around it and reconstruct a dark central shadow. The shadow is larger than the horizon because strong gravity captures light over a wider region and bends nearby rays. Its shape and size depend on mass, viewing angle, and rotation, though current images do not yet determine every detail precisely. Gravitational waves provide another way to study horizons. When black holes merge, their changing gravitational fields send waves through space-time. Detectors measure the final moments of orbital motion and the vibration of the newly formed remnant. The fading pattern agrees closely with predictions for a black hole settling into a stable state. These observations test general relativity under extreme conditions without revealing the hidden interior. The event horizon also raises deep problems where gravity and quantum physics meet. According to classical relativity, information that crosses the boundary cannot return. Quantum theory preserves information in fundamental processes. Black hole evaporation, predicted through quantum effects near the horizon, brings these principles into tension. The resolution remains uncertain because no complete theory of quantum gravity has been confirmed. For astrophysical black holes, evaporation is slow. A stellar black hole would require far longer than the current age of the universe to lose a significant fraction of its mass this way. Accretion and mergers dominate its present development. Hawking radiation remains a theoretical prediction supported by strong reasoning, but it has not been directly detected from an astronomical black hole. At the boundary, darkness becomes a precise physical condition. It does not mean that nothing exists. It means that every possible outward message fails. The surrounding disk may blaze, jets may extend across galaxies, and space-time may ring after a merger, yet the region inside the horizon remains causally sealed. The black hole is therefore known through motion, radiation, and gravity around its edge, while the boundary itself marks the final limit of escape. Inside a black hole, established physics reaches a region that cannot be observed. General relativity describes how space-time curves under mass and energy, and it predicts what happens after matter crosses an event horizon. According to this theory, every future directed path inside the horizon leads farther inward. No signal can reverse course and return to distant space. The equations remain precise, but their deepest prediction eventually enters conditions where the theory no longer provides a description. For a simple, non-rotating black hole, general relativity predicts that collapsing matter approaches a central singularity. A singularity is not an ordinary object. It is a point where quantities such as density and space-time curvature become infinite within the mathematical model. Infinite values usually indicate that a theory has been pushed beyond the range where it can describe nature reliably. The singularity therefore marks a failure of the classical description rather than a confirmed physical structure with known properties. The prediction follows from singularity theorems developed within general relativity. Under broad conditions, sufficiently strong gravitational collapse produces paths through space-time that cannot be extended indefinitely. These results show that the breakdown is not merely an artifact of a perfectly symmetrical model. They do not reveal what replaces the singularity. They establish that classical space-time becomes incomplete under extreme collapse, leaving the final state unresolved. Rotation changes the mathematical interior. Real black holes are expected to rotate because stars gas and merging objects carry angular momentum. The ideal rotating solution contains a more complicated internal geometry, including an inner horizon and a ring-shaped singularity. However, these features may be unstable. Small disturbances and falling radiation can become greatly amplified near the inner horizon, producing a process called mass inflation. Observations cannot test the final internal structure, and realistic calculations remain difficult. Matter crossing the event horizon continues to follow local physical laws for a time. In a large black hole, the horizon itself may not produce severe tidal forces. Farther inward curvature grows and the difference in gravity across an object becomes stronger. Molecules separate atoms are disrupted, and elementary particles may be driven into conditions beyond present experiments. The exact sequence depends on black hole mass rotation and the path of the falling matter. General relativity treats space-time as a smooth geometry. Quantum physics describes matter and radiation through probabilities, fields, and discrete interactions. Both theories are supported by extensive evidence in their own domains. Near the predicted singularity, neither can be ignored. Gravity becomes extremely strong while physical scales become extremely small. A successful description, therefore, requires a theory of quantum gravity, but no such theory has yet been confirmed by experiment. Several research programs attempt to build this deeper framework. String theory represents fundamental entities as extended objects and includes a quantum description of gravity. Loop quantum gravity describes space-time through discrete quantum structures. Other approaches study causal networks, emergent geometry, modified quantum principles, or new relationships between gravity and information. Each provides mathematical insights, yet none has produced a complete experimentally verified account of a black hole interior. Some models replace the singularity with a very small but finite quantum region. Others propose that collapse leads to a bounce, a transition, or a new phase of space-time. These possibilities remain theoretical. Current observations of black hole shadows, accretion flows, stellar orbits, and gravitational waves test the exterior geometry. They do not reveal whether any proposed structure exists beyond the horizon. The uncertainty becomes especially sharp in the black hole information problem. Quantum theory indicates that information about a physical state is not destroyed during ordinary evolution. Classical black holes appear to hide information permanently behind the horizon. Hawking radiation adds another difficulty. Quantum field calculations predict that black holes emit thermal radiation and slowly lose mass. If the radiation contains no detailed record of what formed the black hole, complete evaporation appears to erase information. Many physicists expect information to be preserved, but the mechanism remains debated. It may be encoded subtly in Hawking radiation, stored in correlations that become visible only over immense periods, or represented through a deeper description of space-time. Ideas involving holography suggest that information inside a region can be described by degrees of freedom on a lower dimensional boundary. This principle has strong support in some theoretical settings, though its exact application to realistic black holes remains incomplete. One proposal suggests that the horizon could become a region of extreme quantum activity, sometimes called a firewall. Such a structure would destroy falling matter at the boundary and conflict with the smooth crossing predicted by general relativity. Other proposals preserve a quiet horizon but modify assumptions about locality entanglement or the meaning of interior space. No direct observation currently distinguishes among these possibilities. The interior also challenges ordinary ideas of place and time. Inside a classical horizon, moving inward is as unavoidable as moving toward the future. The central region is not simply a location that can be avoided by turning sideways. It lies along every future path. Language built from everyday space becomes unreliable, and diagrams can mislead when they compress curved space-time into flat images. Despite these limits, the exterior predictions remain highly successful. Black hole masses measured through orbits agree with lensing accretion and gravitational wave observations. Merger signals match the behavior expected from compact objects with horizons. No confirmed evidence requires a material surface or an alternative compact object. Observations, therefore, support the black hole model strongly outside and near the horizon, while leaving the deepest interior untested. Scientific uncertainty does not make every idea equally likely. Any proposed replacement must reproduce general relativity. Where that theory works, remain consistent with quantum physics and produce testable consequences. Most speculative models fail one or more of these demands. The reliable conclusion is limited but clear. Matter crosses the horizon, classical gravity drives it inward, and the equations predict their own breakdown. Beyond that point, present science has possibilities, constraints, and mathematical clues, but no verified account of what the final interior becomes. Across the dark reaches of space, every discovery leaves a boundary beside it. Light reveals galaxies, clusters, stars, and distant explosions. Yet each observation also marks the edge of what can be measured. Gravity shapes structures that remain partly unseen. Matter gathers, separates, collapses, and changes form across timescales far longer than any human life. The universe does not become less orderly because it contains darkness. Cosmic voids follow the growth of structure. Dark matter follows gravity. Rogue planets continue along stable paths through the galaxy. Neutron stars maintain their balance through forces operating inside dense matter. Black holes obey the geometry of space-time even where direct observation ends. What appears terrifying from a distance often becomes quieter when described carefully. A gamma-ray burst is not an unexplained flash, but a signal from extreme stellar change. A tidal disruption is not chaos without structure, but gravity acting across a star. An event horizon is not a surface of mystery alone, but a precise boundary in causal connection. The unknown remains, but it stands beside a large body of reliable knowledge. Space continues beyond every familiar scale. Ancient radiation crosses expanding distances. Faint galaxies send light through regions almost empty of matter. Compact remnants turn in darkness, and invisible mass guides the slow motion of stars. None of these processes requires haste. They unfold according to physical laws steadily and without awareness. The night sky, therefore, holds both absence and record. Darkness hides many details, but it also provides the background against which every photon becomes visible. The deepest regions remain silent while their influence reaches outward through gravity, motion, radiation, and time. The universe continues its long evolution, vast, cold, structured, and calm. End of script. Sleep well.